Okay, thank you. And let us switch to a somewhat more romantic subject. We will speak about, discuss stars in the next 1 hour. And here is just a short list of possible further reading for those who is interested in. And essentially, I will give 2 lectures on this subject. And more or less, the first lecture will be about structure of stable stars. And the second lecture will be about life of changing stars, but with some admixtures, not strictly separated. Okay, so the first 2 textbooks are good because they are written by particle physicists for particle physicists. And therefore, the authors, and yes, this is Steven Weinberg, already mentioned in this school many times, still they use notations understandable by particle physicists. They use a language of particle physics and so on. The third book is much more professional. It is written by astronomers for astronomers, and it is much more detailed. And the 3 papers will be used in the last part of this particular first lecture, just for references, and I will not repeat references on my slides. Okay, so what is a star? To our purposes, a star is a solution of a system of differential equations. And it is for this lecture, it will be a stationary solution, or in any case, it will be a slowly changing solution, an adiabatical solution. But except for a very few moments of life of the star, which we will briefly mention in the second lecture, these equations will be very simple. I will show you a lot of equations, but please feel some warmness when you look at them. They are very familiar. They are very nice. Newton's law, energy conservation, something we remember from at least the first year of our studentship. And so they will be very simple. But stars are complicated. What is the trick? The trick is in the coefficients. The coefficients in these equations encode all kinds of physical processes. And if we change physics, if we introduce some new physics, new particle physics in particular, then these coefficients change, and these equations change, and the solutions, of course, also change. And we will see that for some new physics, for some new particles introduced or new interactions introduced, the stars, as the solutions of these equations, will look differently than the stars we see around. This is the key idea of the approach, which proved to be very successful. And my lectures will be focused on this. Let us start to combine the system of equations to which a star is a solution. And start with the Newton's law. The first equation is just simply the hydrostatic equilibrium equation. Consider a thin shell. Introduce a coordinate system with the sun, in which radial coordinates is measured from the stellar center, neglect for the moment all kinds of deviations from spherical symmetry, and write one-dimensional system of simplified equations. Consider a thin shell between R and R plus dr. It has the mass expressed through the density, so that we will use also this running mass as an integral, as a mass of the ball inside this sphere. And we need to equal the gravitational force and the Archimedes force. You know, and their sum should be equal to 0, because any inner shell in the star does not fly. It is in the between. It is put in equilibrium between two neighboring shells. This gives us the equation of hydrostatic equilibrium, which relates the derivative of the pressure with the gravitation. For the moment, we have two unknown functions, pressure and density, but only one equation, so we need to find something more. Before we proceed, we can speak a little bit about this one radiation, which is essentially just gravitational equation, an equation for the gravitational forces. And we can imagine that we are clever enough and strong enough to take these thin shells, starting from the outer one, from the star, and move them to infinity, one by one. Thin shell by thin shell, spherical shell by spherical shell. And of course, we will need to have some work to do that. And we need to, we can obtain by integration over these removable shells of a star, we can calculate the energy which is required to bring all the stars to infinity. And this is nothing but a total gravitational energy of the star. For each thin shell, which I following the notations of Weinberg, I call it a capital omega, which is probably not the best idea, but okay. So it is the total gravitational energy of the star, which is the integral from 0 to some capital R, which is what? Which is where the star ends. So this is the radius of the very outer star of this, very outer shell of the star, and at which density and pressure becomes equal to 0. This is not a real stellar surface. Okay, we write this omega. We use this hydrostatic equilibrium equation and integrate by parts to get this, to express this omega via the integral of the pressure, with a notable coefficient of -3, which is very important for stellar physics, because the total energy of the star is as the sum of the internal thermal energy of the star. We think that the star is somewhat hot, a somewhat hot object. it's an educated guess. And so there is some non-zero temperature inside, and there is some thermal energy of moving electrons or something else, whatever. And we, in this is the total energy of a star without a relativistic mass energy. We don't count it, rest mass. The fact that the star does not blow up and go to infinity without our help, without our work shell by shell, means that the total energy should be negative. And the total energy is negative when this inequality holds. Now we come to the second equation. We cannot proceed further without the second equation. And the second equation, you remember that we have density and pressure, and we need something to relate them. And this is, of course, the equation of state. And the equation of state, unfortunately, it brings to us the third variable, temperature. Yes? You should remember from the first year, again, from the first year of general physics, that there are some different equations of states, all relate pressure, density, and temperature, and they are often parameterized by the power law, which is called polytropic. And for these guys, for these cases, which cover almost anything, we have this relation for the energy density, internal energy density, and pressure. Substituted here to get a pressure out of the brackets and obtain the stability condition for the polytropic equations. Just from here, I solve this very simple equation, 1 over gamma minus 1 minus 3 less than 0, to have negative energy, and this is the stability condition. Now let us look at these equations of state. For instance, this is the first equation of state we know from the school. For ideal monoatomic gas, this is just this one, I won't read it, and dividing pressure by the energy, we obtain that this value of gamma is 5 over 3. The second case, which we will only briefly touch in the second lecture, is that of non-relativistic Fermi gas. And the equations the equation of state are very different, but the polytropic index is the same. It, however, changes if we consider ultra-relativistic gas, because equation of state becomes again different, and it gives a 4 over 3, and the same for radiation, though it is again a very different equation of state. But this 4 over 3 is problematic, because this is right at the edge of the stability condition. Just note that. For the moment, we do not use it because we still don't have a closed system of equations, because we introduced the second equation of state, which related density and pressure, but introduced temperature. And to understand how we can proceed, how we can go on, what kind of equation of the third equation we need, let us use the virial theorem, which is a consequence of the same gravitational, yes, the same gravitational force. You remember, we started with the gravitational force and wrote the hydrostatic equilibrium. We substituted it to the simple expression, not equation, but just expression for energy, and obtained that relation. So, for non-relativistic gas, we will speak about non-degenerate for the moment, but you remember that the same was for non-relativistic degenerate Fermi gas. We get the virial theorem relating gravitational and internal, that is thermal, that is kinetic energy of an object, our star in particular. And to get an idea where to move further, we imagine how the star forms. The star, how this solution of equations forms in our universe. Everybody knows that we start with the gas clouds, and then we start with the gas clouds, and somehow they condense and produce these rather compact and very hot and shiny objects, which we call stars in the astronomical sense, not in the mathematical sense. Take a cloud of gas, but this will be non-ideal gas, because we should allow particles to collide and to somehow remove energy from this imaginary cloud. Yes? In which way? By radiation, or just by flying particles, but by particles flying away with some kinetic energy. But for simplicity, we assume that the energy is carried by radiation, and then the total energy, of course, decreases. But if the sum of these quantities decreases, then this relation means that the gravitational energy should become more negative, so the cloud contracts, and kinetic energy should become more positive, so the cloud heats. And because it contracts, at some moment it becomes so dense that it is opaque for this, for this radiation which brings energy away. At this moment, the energy losses are still there, but only from the surface. And the idea of a star is that an opaque cloud cannot emit energy and lose energy from its entirety. This means that when eventually the temperature and density in the center becomes so high that thermonuclear reactions start, the energy loss, thermonuclear reaction starts, that means that some energy is produced. But it is produced in the center, and the energy is lost from the surface. So the K moment for the stellar equilibrium, for the stellar life, is that the transfer of this energy from the center to the surface. And this gives us the idea of the next equation. Actually, the next two equations will describe this radiation transfer. Consider again a thin shell at the radius r, and determine, let's define this radial energy transferred per second through this entire shell, 4 pi shell. The dimensionality is, of this quantity is power. And of course, this is just the energy conservation. If we have some energy flux through this shell, then incoming energy should be equal to outgoing energy up to energy production or loss inside the shell, which we loosely denote by some epsilon, which is the energy production minus energy escape per unit mass, just for convenience, because we wrote the mass density here. This is traditional. What is epsilon? Epsilon is that tricky coefficient which depends on everything, on all physics, on all microscopic physical processes there in the star. It includes the thermonuclear energy production, if any, because not everywhere in the star it is thermonuclear reactions go, only in the central part. It includes possible, but normally very, very small contribution from the change of mass distribution in the star. For a stationary, long-living star, it is negligible. It determines the energy carried out by neutrinos, either produced by thermonuclear reactions or just produced thermally in microscopic processes of interactions of electrons, photons, nuclei, and so on. And of course, it can have some unknown contribution from any new physics processes or particles which might be produced. For instance, may compete with neutrinos in energy in carrying energy away from the star. Please note that here I do not include the energy flux by radiation, yes? Because...
Sergey, can I ask a question? Very stupid one.
Very stupid you can, yeah.
Why rho is present in this equation? Why it has to do with the density of the star?
I told you that this is just a tradition. You divide it by grams and multiplied by grams again. That's no, it's not a Russian tradition. It's just astronomers' tradition. We particle physicists, we always prefer to deal with concentrations, and they prefer grams over centimeter cube. That's okay. So imagine we have some very weakly interacting particles which compete with neutrinos and carry energy away from inside of the star. Yes, they will contribute here to epsilon x. That was the original idea behind all this. Actually, the first application of this thing. But we will see that there are more. So we have this equation, which is nothing but the energy conservation. And now, when Emil started asking questions, I was about to say that I do not include here the radiative transfer itself, because I do not include it in epsilon, because it is included in the left-hand part. It is just what we are describing, a transfer of energy by photons. And here we need to write one more equation which describes this energy transfer, which is a little bit similar to the previous one, but for photons. And photons, we can imagine that inside a star, photons do not travel freely like neutrinos. They interact with stellar matter. And they have some mean free path, which we determine in a particle physics way with cross-section and concentration. And we multiply and divide by the particle mass to go to the astronomical notations exactly in the same way. And then the cross-section becomes opacity, what is called opacity coefficient, which is measured by centimeter square, which inherited from the cross-section, divided by gram. And of course, they multiply it back by grams, going through from the concentration to the mass density. We will actually see in maybe some 10 minutes that in some cases it is useful. Okay, how to calculate the cross-section? We know, we particle physicists know very well how to calculate cross-section. Take processes, calculate Feynman diagrams, matrix elements, and obtain cross-sections. We even do not need Feynman diagrams in many cases, because in the non-relativistic regime, the cross-sections may be calculated classically. And this is an example of classical electrodynamic cross-section, the Thomson cross-section of photon-electron scattering. This is not the main contribution to the opacity, but this is just an example to estimate as one of possible processes which limits the photon propagation in a star. So we need to divide it by the mass, and the photons interact mostly with electrons. Why? Because this is the electron mass in the denominator, and the nuclear mass would suppress it. It will go to the denominator as well in the same process and will suppress it. However, if we are calculating ρ, the mass density, we, contrary, can neglect electrons, which are too light. Speaking in terms of chemistry, this means that the number of electrons is counted by the nuclear charge, and the mass is counted by nuclear mass, that is number of nucleons. Then I make a very simple, my daughter is studying chemistry, and since she's not with me here, and I'm not sure how many chemistry students or just chemists are in the audience, I will make a very rough and unforgivable approximation. Because I encode all the chemistry in this simple and approximate relation, which is not exact, but gives us an idea of the relation between charge and mass. Roughly, except for the hydrogen, all nuclei are consisting in equal numbers of protons and neutrons, more or less. However, I keep hydrogen alone because the stars are made mostly of hydrogen. And I would get some, factor of 2 error if I assume this relation also for it. Calculate the number of electrons in this way, summing up over chemical elements. Calculate the number of nucleates in this way, divide one to another, and introduce this X. Large X, capital X, has nothing to do with the small x which I introduced to parameterize unknown unknowns, new physics. This is just the mass fraction of hydrogen in a star. Again, a standard astronomical notation. X is, capital X is for hydrogen, capital Y is for helium, and capital Z is for the sum of everything else. We calculate the Thomson opacity in this way, substitute the rough primordial 3/4, 75% of hydrogen, roughly 1/4 is helium, 3/4 are hydrogen, obtain some number. What for I did that? That I can estimate the mean free path in the sun. With this number, I would need this number to estimate it. Only if I take into account Thomson cross-section, which I told you is not the main contributor to opacity. But already with it, the mean free path is of order 2 centimeters. In practice, it is shorter because of other possible processes of absorption. So, keeping in mind that the solar radius has this value, we see that the mean free path in the sun is much, much shorter. And this means that we can, to some approximation, imagine the radiation transfer in the sun as a diffusion of photons. Very interesting. Before we go, you see, this is what I prepared for the first time for this lecture, and I did not find it anywhere in the literature, actually, in this form. So because it is for the first time, I forgot about it. You see, this is the miraculous Cramer's law for opacity. Once upon a time, I found it a good idea to calculate microscopic opacity for some processes in the sun, starting from Feynman diagrams. And I calculated it and obtained the textbook dependence of opacity over density and temperature written here and called Cramer's law. And in textbooks, you normally see that, okay, come on, this is a law which works for many, many processes. I was surprised and forced myself to calculate another process for opacity. Just Feynman diagrams, matrix elements, all the way to get this one. Again, this relation, but with a different coefficient. Of course, this is a proportionality, yes? So the coefficients are determined by all this stuff, but the temperature and density dependence is just like this. And okay, that was a miracle for me, miraculous, and I could not find any easy explanation of that. Now, I had a long discussion with ChatGPT, and together we elaborated a kind of explanation for that, which is, well, not very good, but still interesting to follow. This Cramer's law, maybe it is written in some textbook, but I did not find. Look, suppose that the absorption process is related to some thermal process, absorption and radiation. This is not the case, for instance, for Thomson scattering. Thomson scattering is completely different, and by the way, it does not follow the Kramer's law. The opacity we calculated previously, it is constant. And okay, then there is a Kirchhoff law, which is essentially equality of emission and absorption. And written in terms of emissivity per unit volume and absorption per unit length, it takes the Planck spectrum as a multiplier. And we see that this Planck spectrum contains nu to the frequency to the third power. And if we write this absorption per unit length, this means that we start to kind of calculate the cross section. And to calculate the cross section, we know that most processes involve two particles. They are scattered. Electrons, photons, they are pair processes. So this should.
Sergey, why do you simultaneously use Planckian distribution and Maxwell distribution? Is it not, why don't you just, instead of Maxwell, use Boltzmann and then...
Of course I can, yeah, of course I can, but this is more familiar for me, for way to understand that there are some heavy particles participating in this.
It is true, because for radiation, the Boltzmann...
This is true because one part is for radiation, another for particles. Why not? This guy goes for particles, for interacting particles, electrons essentially, and it contains temperature to -1/2. Exponents I do not care because thanks to the thermal distributions, we sit close to, with frequencies close to the temperatures, and all the exponents give coefficients of order 1. And we have -1/2, -3 from here to get -7/2. And we have these two concentrations which go to squared density, and we have to divide it by the density to go to astronomical notations. So this density is trivial to understand for pair processes, and this is also a combination of the Maxwell distribution for electrons and the Planck spectrum for photons. Kind of. And what is the assumption? Actually, two assumptions. One is that the process is thermal, so that we can rely on Kirchhoff's law. And the second assumption is that this cross-section is roughly constant and does not depend on energy in the entire energy range of interest. This is true for processes which are most important in stars. They are based on Coulomb scattering, so-called free-free, bound-free, Bremsstraßung, and so on.
I'm sorry, it is Kirchhoff law for radiation from the surface of the star?
No, for a shell. For a shell.
Oh,
Inside. For a thin shell inside.
And usually we understand Kirchhoff law as 1/4 speed of light.
Yes, exactly. But this is another differential formulation of the same thing. We take one surface, second surface, and subtract.
This is something like difference.
Yes. Exactly. Difference between two Kirchhoff's laws. Okay. So How many time do I have?
25 minutes.
Great. We'll probably speed up a little bit. I promised to substitute radiative transfer by photon diffusion. And photon diffusion I will describe, following some textbooks, I will describe as a particle diffusion, which is of course incorrect, but still. For particles we can have a diffusion coefficient, which is determined in a very simple way by velocity times mean free path. And for the velocity, we should take this velocity square question, y squared. Here we have the first power of velocity, but for some reason, I average velocity square. This is a question for homework. And for photon random walk, we simply trade the concentration for the radiation energy density, which is again in the I put here speed of light equal to 1 for simplicity, and so for short mean free paths, of course, somewhere close to the stellar surface, this condition breaks because the star becomes progressively less dense. And okay, we obtain these radiative transfer equations, and happily we see that it closes the system because it has the energy conservation introduced the luminosity flux, L capital. But this does not introduce any new functions because it depends, the right-hand side depends on temperature, which was already.
Sergey, I'm a bit lost. Where are we heading to? What are you now trying to obtain?
A system of a closed system of differential equations for star, and actually I already obtained it because this one closes the system without introduction any new variable. But before showing you at the next on the next slide the system, I have another. I feel another warmness in my heart because it is very close to what we all learned in the school, and it is actually the same physics. If we have radiative transfer and opacities due to different processes, these opacities should sum up. Like a photon can leave its energy in one or another or third process. But if we have energy carriers other than photons, for instance, electrons, the energy flux, the energy transfer can be by conductivity, by electron conductivity, or by anything else. Then we should consider this system of parallel resistors, and the energy flux can go by photons, by electrons, by X particles. So the opacities, the inverse opacities should be added. Now, please enjoy. This is a system of stellar equations. There are 4 stellar equations, and this one is an important relation determining this mass. So this system is nonlinear, as you see, and actually it is strongly nonlinear, but it is a first-order system because we
I'm sorry, the second equation is strange because we know that only two intensive variation is independent, and you write 3. This 3 intensive
No, 4.
No, second.
But they enter everywhere. Here is the chemical, mu encodes chemical composition.
But independent is only two of them, rho or T or mu or T or rho or mu.
We fix mu, of course, we fix mu and relate here. This is they are related exactly by this equation.
When you write this equation, you assume the equilibrium. And in equilibrium state, only two of intensive variables are independent. Only two of them.
This is the equation of state. Yes. Just this is just relation. They become independent when included in the entire system. Yes, this is the system, and yes, as a solution, they will. I will actually tell you this in a moment.
R is the solution of this problem.
Yeah, they all are, of course, function of the radius. We have 4 equations for 4 functions, and this is good in terms of finding. But yes?
Chemical composition also change your...
Yes. For the moment, we suppose that it is all right. It is fixed, and we consider a snapshot of a star with a fixed chemical composition. If it changes, then we know how it changes, and write the 5th equation. You see, I have no place on the slide to write the 5th one, so I skipped it. Okay, boundary conditions, which we need to find a solution. Of course, we have regularity at the center, and remember that we put at somewhere density of the star and temperature or pressure of the star equal to 0 at some unphysical nominal stellar radius. But it is not helpful. If we put the boundary condition on an unknown value of the variable, this does not help much. So in reality, the stars ends much earlier because our equations stop to work in the outer regions of the star where the matter is transparent. And our diffusive approximation breaks, and also many other approximation break. For instance, we can see the stellar radiation from some effective radius at which the temperature is far from being 0, very far from being 0. So how can we treat with this minor problem? We start solve as a system of this boundary value by shooting from the center, by the shooting method. Again, some warmness, numerical methods from second year, shooting. We shoot from the center with these 2 parameters at the 0, and tune them to get at any radius which we want to find desired temperature and density. And this means that this shooting determines a family of solution parameterized by which? Parameterized by a single parameter, which is our arbitrary radius at which we put our boundary conditions. And now the trick. The trick is that once we fix some r, okay, it is unphysical. We don't care. We fix it, find the solution, and with this solution we know everything. We know density and we know temperature distribution. Then replace this parameter, trade it for the observable quantity. For instance, the mass of the star or luminosity of the star or temperature of the star, which we can see from the surface. And so all stars are parameterized by a single parameter, which can be, for instance, mass. In mass formulation is especially easy and successful because we can make a substitution of variables like that, and we obtain very well defined boundary conditions because we know the mass of the star. We do not know at which radius it saturates, but we don't know to need this radius to get boundary condition. And this is a well-defined system of differential equations, 4 equations, 4 functions, 4 boundary conditions, but as in any other nonlinear system, nonlinear boundary value system, theorems of existence and uniqueness of solution do not work, and we are not sure that the solution is unique, and which is especially important for us, that it exists. This means that even with these nice boundary conditions and equations, we can make new physics contributions to these epsilon or, oh, sorry, it is a misprint here, it should be kappa, not chi. This is opacity, this is energy production or loss. We change them we can change them in such a way with our new physics that the star does not exist any longer. Here it is written what physics can be put inside. We can change nuclear reaction rates. It is not called new physics, yes, because nobody measures precisely nuclear reaction rates. We can change the associated neutrino production in the central parts. So we can change epsilon nuclear and epsilon neutrino in the central parts easily. We can add a known matter to a star which will change the mass distribution so that we will touch epsilon gravity. Or we, as I have just mentioned, we can put weakly interacting new particles which escape the star and help neutrinos to carry energy away, touching epsilon x. For the opacity, also we can modify photon cross-sections which are responsible for the radiative opacity, or we can introduce a new channel of local energy transfer. Look, if the new particles have very small cross-section with the stellar matter, they flow away and carry energy away and contribute to epsilon. If they interact rather strongly, they have small mean free paths, they contribute to opacity, to the local diffusive energy transfer. And of course, the maximal effect is in the very hard to study range regime, where the mean free path of the new particles is of order the solar radius, stellar radius. I will switch to the sun soon, so I already, it is a star anyway. The stellar radius, then energy is efficiently transferred from one part of the star to another and change physics rather strongly. A toy example, after which I will probably stop, or I stop now to leave some time for questions.
Still have 20 minutes.
20 minutes, perfect. I don't stop. I never stop. Okay, so at least this toy example I can discuss safely. Assume that there is a new channel of energy loss, but for simplicity, we think of it as being proportional to the nuclear energy production. So essentially, the new epsilon is just a modification of the nuclear energy production by some coefficient which it decreases it. And I neglect neutrino energy losses and gravitational energy losses. I assume Cramer's law, which we know is very good. And then I use that the thermonuclear reaction, for thermonuclear reactions, this is power for any reaction, at least what is relevant for stellar burning, this epsilon energy production rate per unit mass can be written by this power, these two powers. For the main hydrogen burning chain in the star, for instance, in the sun, this is the coefficients, the power laws are like that. And okay, then every changes are encoded in this power law, and we can assume, and this assumption is good, provided that these functions, epsilon and kappa, are power law functions of density and temperature, then all the changes in the star can be obtained by scaling with some parameter, scale parameter, which we call y for the moment, and we don't know what is it. We shall use stellar equations to find y at the next slide. But just let us stop for the moment, for a little moment, stop and think. What we are doing? I'm telling you that I take a star, find the solution, and then I switch on new physics. This is, of course, not true. I simply compare two solutions, one with new physics and another without new physics. But I speak in the form that like I switch it on. And consider I switched small delta and the star changed. Of course, these are two different stars in two different universes, but I will compare them, just not to mix. If I say that something changes, yes, total mass and chemical composition do not change, and the radial scale changes. This means that they do not change with time. They differ from one real star to another imaginary star. So I substitute everything, this simple scaling to my equations, my stellar equations, one by one. I start with the hydrostatic equilibrium to obtain scaling of density I obtain just from this, dividing mass by r cube. I substituted to the hydrostatic equilibrium and obtain scaling for pressure. I use equation of state for simplicity, just very simple, obtain scaling for temperature. Use energy transfer and energy conservation, because it is a closed system. I can use both now to obtain scaling of L, of the flux of energy. And of course, these coefficients should be equal. I equal one to another and obtain y. What is important for us is that y is smaller than 1. The exact coefficient doesn't matter. It is smaller than 1, which means that when I substitute this y back to my scaling relation, we see that star becomes a bit smaller, a bit brighter, not minus here, plus here, plus here. A bit smaller, a bit brighter, a bit hotter. It does not become, yeah? The virtual star is a bit smaller, brighter, and hotter than the real star. How can this happen? How can it become brighter? Yeah, just brighter. it loses more energy to radiation. That means that it produces more energy in the center. So the consumption of nuclear fuel becomes faster. And unfortunately, this virtual star lives shorter. If we consume our fuel faster, we live shorter. That's the energy conservation. Okay, the sun exists still. And just from this fact, we can obtain constraints on new physics. Because the sun roughly spent half of its lifetime. Maybe it will disappear tomorrow. It's all right. Well, not perfect for us, but for these equations, it would be all right. But at least half of its lifetime, it already spent and did not die. And so we obtain this very rough constraint, that the contribution of extra energy losses is not more than 1/2 of the nuclear energy loss. This means that by these constraints, we can allow that the sun produces 2/3 of its energy in photons and 1/3 in something else, which we do not see and never will see. Okay. The first amazing point about this condition is that, look, it is fantastically rough, very rough. 1/2 of energy, well, we think the sun is just a well-studied object. 1/2 of its energy, 1/3 of its energy can go for some new physics. What can you constrain with that? You still get constraints on many light particles, light and weakly interacting particles, 4 to 5 orders of magnitude better than laboratory experiments. We will see next day that the solar constraints are not strongest among astrophysical constraints. But all astrophysical constraints obtained in this or similar ways are 4 to 5 orders of magnitude stronger than those we obtain with our particle physics experiments. Even this one, even this very, very rough constraint. And the second amazing question is, why so rough? Why? We know the sun very well. It is very close. We observe it for several millennia, or maybe millions of years. We do observe and accumulate our knowledge. And okay, the answer why we can allow for some really huge energy losses is the degeneracy of model parameters. And at this point, I temporarily allow the star to live, to develop, to evolve. And consider changing of this. These were stationary equations, so describing a star at a particular moment of time. What changes with time? With time changes again epsilon and kappa because of the thermonuclear reaction, and also changes chemical composition because of thermonuclear reaction. So to start with, to find a solution with some evolving sun, we need to start at 0 time with some chemical composition. So we should state that there was some amount of gallium or other metals. Essentially, gallium is important for us. And also we need to tune one more parameter, which I completely skipped. I completely skipped the story of convection, yes? So I put conductivity and radiation transfer, but there exists some convection, of course, which is much harder and unfortunately cannot be described with these Newton law and energy conservation equations, kind of, so I skipped. Okay, so we need one parameter there, and starting chemical composition, essentially how much gallium and how much hydrogen is there. And we need it to tune observable luminosity and the mass or radius of the sun. And changing a little bit the chemical composition and this second guy, we can obtain the present day sun, luminosity and mass for different lifetimes. However, for that short lifetimes, the solution stops to exist. I told you that we are not obliged to have a unique solution or to have a solution at all. And if we change the sun so dramatically, then the solution still simply does not exist. I stop at this moment because the next part I will skip to the problem. At the next lecture, we will dig into the sun to get more details, to go beyond this approximation. This we will do next time, and should be a problem somewhere. A problem. Thanks.
Thank you very much for your interesting lecture. And I think I can ask many questions about thermodynamics in the astrophysics. But I ask two. First one, on the 9 slides, when you described energy transfers, I think one energy transfer must be added. Particles of the sun's matter can have speeds higher than first space speed. And during the heat transfer inside the sun, its matter flies.
Yes, mass loss. It is called mass loss. And this may be important, especially at late stages of stellar evolution, and it is not included in this thing. But of course, this is not a dramatic effect on the stellar structure because they can escape only from the surface.
Okay. I just thought that you said 1/3 of energy is unknown. And
No, I don't say that. It is allowed. It is allowed to carry out 1/3 of energy by this argument. We will see that more detailed arguments will constrain it stronger.
Okay, thank you. And second question, you said we consider sun as a closed system, but why we consider that if it's open system?
Just for simplicity.
Well, that's very big. I think
It is not particularly closed, but because we allow the radiation to escape, we allow neutrinos to escape. We did not consider the mass loss you mentioned, but in principle, good full numerical solution do that, also take it into account. Well, we don't consider anything falling on the star unless we are well, we are studying binary star or something else where it's.
But aren't you confusing closed system of equations, closed star?
What?
Closed system of equations is closed star. I think it's like two different things.
No, I mentioned open and closed system of thermodynamics.
Yes, but
The star is open because it emits energy.
Yes.
That's it. And I was speaking about closing the system of equations, so that the number of variables is equal to the number of equations. That I meant.
Okay, so every distribution in your presentation was for closed system, yes? For closed thermodynamics system.
closed system of equations.
Closed system of equation. No, it cannot be so because we need we need the net energy leaving the system. Yes, it is L capital. L capital leaves the system, so it is an open system in the thermodynamical, from the thermodynamical point of view.
Okay, thank you. Thank you.
Thank you for your lecture. What are observational problem with stars?
Next lecture.
And in other words, what new physics is trying to solve?
Next lecture. Sorry.
Thank you for your lecture. On the page 12, when you wrote the proportion of kappa with temperature, yes, which perturbation, which order of perturbation and expansion did you use?
When I was crazy enough to calculate, I was younger. And first order, still, but not too young, and I used the first order, the leading order, 3 level.
Do you know why your and these results are different?
They are not different.
Somehow.
They are not different. I obtained exactly this Cramer's law, and that surprised me.
Okay.
That surprised me because my calculations were quite involved, and this law is very simple and universal.
Thank you very much.
Thank you for the lecture. We have Cepheid stars, and do we have any problems to solve this system of equation and energy production for Cepheid stars?
We have, because we need we need to take in the opacity coefficient, we need to account, and in the energy balance, partial ionization. So the energy can go, we consider that somehow that energy moves. And it can be absorbed and emitted by means of partial ionization in the outer shells of the stars. And this governs Cepheids. So this we don't take. But Cepheids are not stationary solution. We also skipped gallium flash and some other fixed moments in the stellar lifetime.
Thank you for your interesting lecture. I want to ask you about the constraints on delta. You put it 1/2 because we think that the lifetime of our sun is about 8 billion years, and 4 billion years it lived yet. But what if when we change this model, we also need to change a history of sun? Maybe.
Yes, that is what I said. That is why it is so rough approximation. We can do it. We can shorten lifetime by changing initial conditions and convection. But then at some moment, when we reach roughly half of its lifetime, we just cannot solve the equation to produce the current present-day luminosity. We can do what? We can put more hydrogen to burn faster. Yeah, to burn faster, we need more fuel. We put more hydrogen, less gallium, and then at some moment, the hydrogen ends. Yeah, and we already burnt all the hydrogen, or a significant part of it, in the center, so that the luminosity of the sun would not be reproduced.
Thank you.
Thank you for the lecture. So you said that we can obtain some new physics, for example, in epsilon x that you call, for example, new particles, if they exist. But our equations, mostly the equation of the thermodynamical equation, of the connection between rho and B, the choice of this equation of state is have a big error. So can we really obtain some new physics and see new particles? Because we have a very big error of all these computations because of this equation of state.
As you see, the errors are not that big, and even 1/2, the error of 50% allows us to constrain some new particles. Okay, 50% error in the lifetime of the sun. But of course, this changing something in this system of equation, the point is not in the errors, but in the degeneracy. Changing something in this system of equation, you can easily fail to satisfy your boundary condition, like with any boundary value problem. That is the point, and that allows one to make even more precise constraints.